Welcome to qnawire.
So this question asks us to show that the average kinetic energy of a conduction electron in a metal at 0 Kelvin is equal to 3 over 5 multiplied by the Fermi energy shown by the expression in this red box here. We are given an equation for the average kinetic energy with this big integral to solve. We are given the number density of states given by this expression here. And we also know that the number density of the electrons is given by this expression here. So the first point to note is that we are only interested in states with values between 0 and the Fermi energy, because for the purposes of this, it's impossible to have any particles in states above that value, because the Fermi energy represents sort of the highest energy level that we can go to at a temperature of 0. Another thing to note is that the denominator in the expression for capital N is actually the Fermi-Dirac distribution, which we will call lowercase f e. And the key thing to note about the Fermi-Dirac distribution is that it always takes a value of 1 at 0 Kelvin between the range of 0 and the Fermi energy here. We can use that to our advantage because it simplifies the integral quite a lot. So we'll start by saying that, also apologies in advance about my handwriting, I'm trying to write this out with a mouse, that our average kinetic energy will be equal to 1 over our number density n subscript e multiplied by the integral, and remember we're only interested in values with a maximum of the Fermi energy and 0. Taking into consideration that our Fermi-Dirac distribution is 1, this just comes out as E multiplied by, well, we have our constant C times by e to the half. And as you can see, that's the only thing that's left in this expression for the number density of states. Obviously, with respect to E. So bringing our constant C out to the outside of the integral and combining our E factors, we end up with an expression that we have to integrate for e to the 3 over 2. And that comes out as, well, our constants will stay there where they are. So we have c over ne. And now we need to add 1 to this power, which will make it 5 over 2, and divide by that power. So that ends up with a 2 over 5 at the front. When we evaluate this expression at 0, it will just be 0. So we only need to consider the first term with EF in. So remember, we've added 1 to the power, so all that comes out will be EF to the 5 over 2. So all we now need to consider is this secondary integral to obtain an expression for the number density Ne. And this will follow a similar pattern to us working out the previous integral. Only this time, the difference is that we will just have this ce to the half rather than this additional e factor here. So that comes out as ne is equal to c, the integral between the Fermi energy and 0, e to the half de. And of course, this will equal, well, we add 1 to the power and then divide by the new power. So half plus 1 is 3 over 2. Dividing that gives us 2/3. C, we only are interested in the Fermi energy term. EF to the 3 halves. So now what we want to do is we want to substitute this expression for Ne into the expression for our average kinetic energy to get it into the form that we need. So E average will be equal to, what we end up with 2/5 divided by 2/3, so that is multiplied by 3 over 2. We just flip the fraction. And then we have the C's will cancel, leaving us with EF to the 5 over 2 over EF to the 3 over 2. And as you can see, our 2's here will cancel, leaving us with the average kinetic energy to be equal to 3/5. And then reducing these powers down, we end up with 3/5 times a singular factor of the Fermi energy as required.